Hi there, this is your favorite non-Indian math channel, and I have an interesting method that used 3000 years ago by Babylonians to calculate square root of numbers. Okay, so in this video we will show that how to show this an will converge to square root of p. Okay, well, it's pretty interesting. How could they come up with that? They don't know anything about sequences, limits, but they could show that this is true. Of course, they couldn't show, but they just said they use it. For example, if you put p is equal to 2, and you can actually pick any a1 value, okay? You can pick anything, but it should be positive. So you can say AP is equal to A, it's positive, and then it will fastly converge to square root of pi, square root of P, okay? So let's see how we can do it. So if we have a recurrence relation, and to be able to show that it's convergent, we can try to show if it's increasing or decreasing, and if it's monotone, if it's bounded, then we are done. First, let me show you an unofficial way. This is just to see if there is a limit, what would it be, okay? So if there was a limit, okay, so this is an unofficial part. If you do this on your paper, then you should delete it, okay? And so if I take limits of all sides, limit of an plus 1 is going to be equal to limit of an. And so if I say this limit is L, okay, so L is going to be 1 over 2L, and 1 over 2. So this is going to be L, P over L. So this is going to be L over 2, P over 2L. Then I could say just P is equal to L squared. So L is actually square root of pi. Okay. So this indeed proves that if we had a limit, it would be square root of pi. But we have to prove it. Okay. This can be an engineer way to solve it. Okay, so engineers can live here, and as mathematicians, so we need to prove it. So, well, there are technically three ways that either this sequence can be increasing and bounded upside, like bounded up from this thing, or it can be decreasing and bounded below by this thing. Okay, which means that it's increasing, for example, and it's going up to square root of pi, or it's decreasing. Okay, of course there are no values at the negative part, and it's going to square root of pi. Okay, again, or it could be making oscillations. I don't know, it could be like this. So, well, if it's the third case, you need to show that it's Cauchy sequence. Okay, it's well, it's not going to be in this case. For example, for this example, we will see which case is it. Okay, let's say 1, 2, 3. So these are the main three ways that it can be. So let's see if I can say that maybe an is less or equal than square root of pi. Okay, I don't know if this is going to be true, or if an maybe it's going to be greater or equal than square root of pi. Okay, how can I do that? Is that I can just say it's easier to show that an is greater than square root of pi. Well, it's of course easier to show that an squared is greater than pi, and it's even easier to show that an squared minus pi is greater than 0. Okay, and this would be same as saying an squared minus pi is less than 0. So I will just check an squared minus pi, is it positive or negative, and I will just pick either it's this is actually second case, and this is first case from this analogy. Okay, so let's check what is an squared minus pi. Well, instead of an squared minus pi, I can just check an plus 1 squared minus pi. Okay, and so I can just substitute it here, squaring this thing 1 over 4, and it's going to be an squared plus p squared over an squared, and it's going to be plus 2p, and of course I have minus p. then well, I can say it's going to be equal to. So here, if you look, if I just extract the last term, okay, it's going to be p over 2, and I have minus p. So if I actually gather it again in the parentheses, it's going to be p squared over an squared. So again, so it's going to, this thing is just, if I multiply it by the 1 over 4, it's going to be p over 2, and p over 2 minus pi is minus p over 2. And if I take it again into parentheses, it's going to be minus 2 pi times 1 over 4, okay? And by the same thing, I mean, this is only this sign changes, and this is actually, now it's an minus p over an squared, okay? So, well, this is something squared, and this has to be greater or equal than 0, and we are done. Okay, look, so I found that an, so this thing is positive, okay? So this means that we have the second case. Well, here it doesn't matter if we have equality, it doesn't matter. Here it can be equal, yeah, well, it's all right. So I know that this is true, okay? For each n, an is greater or equal than square root of pi, okay? But here you should also notice that a1 doesn't have to hold this condition, because we are setting up a1 separately, okay? We can pick anything, but even the a2, like a1 doesn't have to be greater or equal than square root of pi, but even the a2 is going to be following that, okay? This is true for any n greater or equal than 2, okay? So the first result is that we found that it looks like the second form, okay? It looks like the second form here. So it has to be decreasing, okay? Now we will also show that. So we found that an is greater or equal than pi. Sorry, square root of pi. For n is greater or equal than 2. So this is our first result. And the second should be about monotonic, okay? So, and for that, I can just check an plus 1 minus an, okay? And so an plus 1 was 1 over 2 an plus p over an. So I have minus an. And this is going to be, so I have an over 2 and minus an. So it's going to be just negative. And I'm going to have p over an. So this is in 1 over 2 parentheses. And I have minus an over 2. So I can just put an here. Okay. And if I look at my first result, okay, here, if I just multiply both sides by an, okay, so it's going to be 1 over 2 p minus an squared over an. And from this result, I know that if I take an squared, let's write it like this, an squared is greater or equal than pi. So p minus an squared is less or equal than 0. So I know that this is, so this top part is less or equal than 0. But I know that an is positive because any value is positive, and I'm only putting positive values, okay? So there's no reason that any an is going to be negative. So this is positive, and this is less or equal than 0. So 1 over 2 is just a constant. So I know that an plus 1 minus an is less or equal than 0. This means that our sequence is actually decreasing, okay? So this is our second result, okay? So let's again go back here. So I found that it's decreasing. Let me draw a bigger shape. Sorry, there are no values, negative. I showed that no matter, I can just pick one value. Let's say I pick here, and other ones are just gonna decrease, and it's gonna go at most square root of pi, okay? I found this is true, but I don't know if it converges. And now I can do this thing actually, because I know that it's decreasing and it's bounded below, so it has to be convergent. Okay, this is an important theorem. And now I can just say let limit as n goes to infinity, an is equal to L. And I can do literally this thing, okay? So now this is fair, and I can find L is equal to square root of pi. Then I'm gonna find L is equal to square root of pi, okay? And this is how to prove